Firstly, I would like to introduce myself to the audience. My name is Harald Müller. I'm a full professor for building materials and concrete structures. I retired 2.5 years ago, and I'm still a member of the faculty, of course, and have some PhDs, but no longer responsibility on the large institute. And meanwhile, I'm a CEO in a private company with 50 engineers. Well, I have the pleasure to chair this afternoon meeting on, I already mentioned it, on materials and structures. And I have two co-chairmen, and I'm pleased that they will assist me. This is Dr. Arnaud Perrault and Dr. João Pacheco. I would like first that you introduce yourself also a little to the audience.
Thank you, dear professor. So my name is Arnaud Perrault. I'm an associate professor at the University of South Brittany. My research topic deals with rheological behavior of cementitious materials, and I'm recently working on 3D printing of concrete.
Very good. Thank you very much. And João, you're?
Hello, Professor Müller. Hello, everyone.
Hello.
I'm going to introduce myself. I'm a researcher at IST, the University of Lisbon, where I did my master's and my PhD. I work on structural safety based on the Euro codes and on recycled concrete.
Okay, thank you very much. So I think we constitute a very good chairman jury for this meeting with our different backgrounds in research. Well, already I think we take fully pattern of what has been done by György Balázs in the morning meeting. I think you have seen it, and he proposed in his meeting, and I would do the same, that I start with chairing the meeting, and then we should be flexible. The second or the third one may be, you may guide or may be the main chairman for the other presentation. So I think we should split up a little bit this business for chairing this afternoon session. As mentioned repeatedly, we have the contributors, the PhD students, having the chance to present their PhD, the current PhD work, for 15 minutes, and we have 10 minutes for discussion and 5 minutes for everything what is necessary as well. And we have in total 5 PhD students, and as far as I see, all the PhD students are there, so we have a full program this afternoon. And if there is nothing else to say from the maître of ceremony, Farid, hello, then I think we would start with the first presentation. Lukas Gebhard, he is from Switzerland, and he is doing his PhD under Professor Kaufmann in Zurich. So the title of the presentation is Experimental Investigation of Reinforcement Strategies for Concrete Extrusion 3D Printed Beams. The floor is open for you.
Thank you very much for the introduction. I will start to share my screen. So, all right. I hope you can see the slides.
Yes.
Perfect. All right. So welcome to my presentation. As already mentioned, it's about the experimental investigation of reinforcement strategies for concrete extrusion 3D printed beams. First, a few words about the authors. So there's myself and Dr. Jaime Mata-Falcón, and my supervisor, Professor Dr. Walter Kaufmann, from the chair of Concrete Structures and Bridge Design. And this work has been done in collaboration with Anna Anton and Professor Benjamin Dillenberger from Digital Building Technologies. To get started, a few words about digital fabrication with concrete. There's been a lot of interest from industry and universities around the world, and various technologies have been developed. And today I'm going to focus on the most significant technology, or the mainly used technology, so-called concrete 3D printing, where an object is produced without a formwork by the consecutive placement of concrete layers to build this object. In that area, a lot of progress has been done on the material and technology side, and a lot of structures have already been built. However, most of these structures have low structural demands, and their structural behavior is closer to that of masonry than actual structural concrete. And that's why we need reinforcement strategies to have a positive impact on the construction industry. There are, of course, already a lot of projects also in that area. I want to introduce a few here. For example, external reinforcement for this printed truss by the University of Naples, or the reinforcement of the printing filament with a high-strength steel cable at TU Eindhoven. Also at TU Eindhoven, the pre-stressing of a bicycle bridge to keep it in compression, and the use of the concrete only as lost formwork, which is already done in industry, where the reinforcement is placed afterwards and conventional concrete is cast around it. Also, there have been some developments in the field of fiber reinforced extrusion. So, for example, on top you see a small sample extrusion for fiber reinforced concrete, and on the bottom, development of strain hardening cementitious composite with fiber reinforcement, also extruded. And on the right, a few more novel reinforcement approaches perpendicular to the layers, where reinforcement is introduced after the concrete printing and has these short reinforcement parts. So based on these, there is a lot of development and also some testing, but most of the tests are still on a laboratory scale. So only a few tests have been performed on a large scale, and I want to introduce some of the tests here. So also this bicycle bridge at TU Eindhoven was tested in 4-point bending as a scaled down version. Also a pedestrian bridge by a company from Japan, Taisei Corporation, and a simplified version of the truss that we have already seen with external reinforcement was also tested in 3-point bending, and a topology optimized girder tested at Ghent University. And these tests have mainly been performed on really specific geometries for a specific use case. So it's hard to make general assessments from these tests. And that's why in our experiment, we want to look at reinforcement strategies for beams, and we look at different longitudinal reinforcement and different transversal reinforcement, so shear reinforcement. And the general idea of the longitudinal reinforcement, since it will take the main loads in bending, is to have a system which has already proven itself in the industry, so conventional reinforcement or pre-stressing. And for the transversal reinforcement, we wanted to look into more innovative solutions, which are particular to 3D printing, where we reinforce the 3D printing filament itself. And one approach was the cable reinforcement, which I already introduced. And the other one is a reinforcement strategy, which we have recently been developing, so-called aligned interlayer fiber reinforcement, where compared to the other fiber reinforced extrusion, we aim to not extrude the fibers and the concrete simultaneously, but rather extrude the concrete and place the fibers in the second step in between the layers. This allows the use of larger and less expensive fibers, and gives also flexibility in the amount of fibers that can be placed. And these ideas were then translated to a set of beams, which we tested in 4-point bending. Here, just a quick introduction of the reinforcement strategies, and afterwards I will introduce in more detail how we did these tests. So we did have one series where we used unbonded post-tensioning, which was achieved by these threaded rods that you can see here. And then we had conventional reinforcement, so conventional passive reinforcement, which was placed after printing in these voids down here and then grouted. And the two transversal reinforcement approaches, one was cable reinforcement and the other one the aligned interlayer fiber reinforcement. Now, for the experimental campaign, we had two different series, as already mentioned. So the first series covers the post-tensioning with unbonded post-tensioning reinforcement. We produced 4 beams, always one set with transversal reinforcement. Here we used fibers at a concentration of 0.3%, placed only in the webs of the beams, and always an identical beam without this transversal reinforcement. We also looked at 2 different post-tensioning configuration. One configuration was a continuous or a homogeneous post-tensioning with -9 megapascal over the entire cross-section. The other one had -9 megapascal at the bottom and -3 megapascal on top, resulting in -7.5 overall. And the final geometry can be seen on the left with a cross-section with 30 times 15 centimeters and a span of around 1.4 meters. The second series used the conventional passive reinforcement with the grouting, so bonded passive reinforcement. We produced 5 beams. We produced 2 unreinforced beams, 1 beam reinforced with cable reinforcement as transverse reinforcement, and 2 fiber reinforced beams. And here the fiber reinforcement ones was 0.3% and one's 0.6%. And as you can see, the cross-section is slightly increased for these beams. So here we had 32 times 20 centimeters, and we printed 2 filaments, not just 1. And also the span was increased to 1.6 meters. Now about the production and our 3D printer. This 3D printer is an ABB robot on a 3-axis gantry and is fed 2 materials by 2 progressive cavity pumps. And then we have this extruder tool that you can see on the right on top, where we have the big hose for the mortar and the small hose for the accelerator. And this is a set-on-demand system where we have the mortar as Portland-based cement mortar and the accelerator as a calcium aluminum cement paste. And then we printed these beams. And just to say, this is just an exemplary column. These are not the beams that we tested. And we also tested the compressive and tensile strength of the concrete, which was around 7 and 2.4 megapascal respectively. And then we used this system to actually print our beams. So on the left 2 pictures, you can see the print path and a print image from the beams of series 1. So you can see that we have the 1 void in the middle, and we only printed half beams for this session. So we always printed 2 half beams without transversal reinforcement and 2 half beams with transversal reinforcement. They had a layer height of 5 millimeters, and there was 1 filament with a width of 45 millimeters and a printing speed of 150 millimeters per second. The series 2 was produced by 2 filaments, and we did avoid the printing of only half beams. So we printed the entire beam in one go. Again, a set of an unreinforced beam and a reinforced beam. This layer height was the same with 5 millimeters, but the filament was reduced to 25 millimeters, and the printing speed was 160 millimeters per second. Now, for the transversal reinforcement, here some impressions from the placement of the fibers. So all the reinforcement was placed manually to have a good control over the amount of fibers and cables placed. And the fibers were prepared before the printing on these magnetic strips with a plastic foil to have a faster placement of the fibers during printing. The cable was pre-bent to fit the shape of the concrete cross-section, and the fibers were then placed. As a cable, we also used a high-strength cable with an ultimate tensile load of 1.3 kilonewtons, and as fibers, we used conventional N-Took fibers type Dramix 3D 6535. Now, after printing, we had to do a few additional steps in order to be able to have good measurement. So one important part was the use of mortar beds, which you can see here in one, which had to be cast in all areas of load application due to the irregular surface of the 3D concrete printing. Additionally, we used digital image correlation to have a full field tracking of the displacements of the surface, where we applied a thin gypsum layer to have a smooth surface, then painted it white and put black speckles. And we also had to place the longitudinal reinforcement here, exemplary for series 1, where we have the 2 post-tensioning configurations. For series 2, we had the passive reinforcement, which we placed and then grouted. So this gave us this final testing setup, on the left series 1 and on the right series 2. Now I want to show you some impressions from the test. So this is series 1, so we have the unbonded post-tensioning reinforcement. Both videos on the left are without reinforcement and right is with fiber reinforcement in the web. So this video shows you the failure of the beam. So we see a explosive failure of the beam because we have no bond between the concrete and the reinforcement, and we also don't have any reinforcement in the concrete itself. Now, when we added the fibers, we achieved again a brittle failure of the concrete here in the compression zone, but the overall structure of the beam stayed intact, so no catastrophic failure. And the same could be seen for the series with the different post-tensioning, where we had a total collapse of the structure without reinforcement and bending failure for when fibers were present. Just to mention, this is the backside of the beam, so we do not see the digital image correlation surfaces here. But we use this digital image correlation surface to produce these crack patterns here on the right. And on the left, you see the load deformation curves. So again, only series 1, where you can see the 4 beams. We have the unreinforced one here, fiber reinforced one, and then the different post-tensioning configuration on top. And what we can see is that they all behave quite similarly. And if you look at the crack pattern, we see that we mainly develop bending cracks. For beam 111, you can see that the cracks turn slightly to the right. This was mainly caused by some torsion we had in the system, because for the first beam we did not have sufficient out-of-plane stabilization for the beams. What we could also see was that all the beams failed brittly at their ultimate load, and the ultimate load could be increased in both cases when fibers were present. However, since we only developed these bending cracks and no shear cracks, the fibers could not really be activated as shear reinforcement. On the other hand, for series 02, we can see again the load deformation curves on the left with the midterm deflection and the force applied, and on the right, the crack pattern where the line thickness indicates the crack width. If we go from bottom to top, we see the two unreinforced, the behavior of the two unreinforced beams down here, where they have around 100, at around 100 kilonewton, they start to form diagonal shear cracks, and they only have these single shear cracks, which open quite largely, which you can see on the right for the two bottom figures. All of these beams developed multiple bending cracks. However, since these cracks were significantly smaller than the shear cracks, they're a little bit hard to see in this display. For all beams where we had shear reinforcement, the load could be significantly increased. So the first increase you can see for the 0.3% of fibers with the formation of multiple diagonal shear cracks. So this time our shear reinforcement could be activated due to the bond between the conventional reinforcement and the concrete. And then the cable reinforcement with only 0.1% was able to increase the force even more than the 0.3% of fibers. But there were less diagonal cracks and the cracks were slightly more open. And on top, we see the beam with the highest ultimate load, so with 0.6% of fibers. Here it needs to be mentioned that only the right side of the beam was fiber reinforced. That's why we had external shear reinforcement on the left side to provoke the failure on the right where we had the fibers. And also we could not double the ultimate load for double the fiber amount. So what we could learn from this experimental study. Here you see exemplary a beam of series 1, where we could see, of course, we had a enhanced load bearing capacity due to the post tensioning, as you would expect. However, we only developed bending cracks since the reinforcement was unbonded and the shear reinforcement was not activated. So we had a simple truss with a highly brittle failure. And when fibers were present, the ultimate load could be increased and the overall beam stayed intact. For series 2, we could see that the behavior was quite what we would expect from a monolithically produced beams, so the layering seemed to have really little influence on the overall structural behavior. We did develop multiple bending and shear cracks and could activate the shear reinforcement. All the beams failed again brittly in diagonal tension, which was, however, in this case intended since the bending reinforcement was quite over-dimensioned to provoke this shear failure. And both cable and fiber reinforcement enhanced the shear resistance significantly. The fibers had a higher efficiency, so for cases where the ULS is decisive, this could be a good approach. However, for the cable, we still need to look closer at the bond between the cable and the concrete. And for the fiber reinforcement, they were less effective than the cables. However, we had thinner and closer spaced cracks, which could be beneficial for some serviceability applications. Now, an outlook from what we're looking at next. So one problem, of course, with this reinforcement approach is the straight rebars, which limit the geometry. And here we want to look into more curved applications, such as curved post-tensioning cables. Also, all the reinforcement was placed manually, so we want to look into automation of the reinforcement placement. And currently, we have an ongoing study on the detailed study on the crack kinematics to assess the performance of the shear reinforcement. And of course, all of this was not just me, it was a big team behind me, not only the co-authors. So we had the structural lab at ETH and the robotic fabrication lab. From the concrete lab, I want to thank Heinz Richner and Andi Deusser, and the material scientists behind the development of this material that we used, Lex Reiter and Tim Wrangler, under the guidance of Professor Robert Flood. And the project that you see here have been part of students' projects, so I want to thank Jonathan Ansling, Mort Studer, Jean-Luc Imhoff, and Vanessa Studer. And of course, also thank you for the funding of the NCCR for digital fabrication and the SNSF. Thank you very much for your attention.
Thank you very much for this very interesting, very clear presentation. You have been pretty well in time. We started a little late to say, so we are a little behind the schedule, but this was due to the introduction by myself and my co-chairman. So there are already some questions from the audience. Firstly, I was wondering about the low tensile strength you had measured. With a compressive strength around about 70, you measured only 2.5. What's the reason for that?
Yes, so that's also something we have been curious about. We did the measurements of the tensile strength on double punch tests. So we did already see that for many digital fabrication concrete that we have lower tensile strengths that we would expect. However, we only use a maximum aggregate size of 2 millimeters. So we really have a fine-grained mortar, which could contribute to this low tensile strength of the concrete.
Nevertheless, there remains a little bit of question. I have asked this question because tensile strength is decisive for the shear behavior.
Yes.
There is a big interconnection, so this was the reason. And the second point, also very quick, maybe answered by you. I was wondering, when going through your paper, why you have two different dimensions of the beams. Why you have done this?
Well, it was two reasons. So with the first ones, they were quite slender, so we had a little bit out of plane problems, as you could have also seen with the one beam. So they tried to go out of plane a little bit. And the second one is that we had these two voids for the second beam, so we wanted to have a considerable void to place the reinforcement. So the two were, Series 1 was first developed, and then with the lessons learned from Series 1, we went for the design of Series 2. So it's been like an improved series. Okay,
this is clear. Thank you very much. But it makes it a little bit difficult for the reader of the paper if you uses your curve, your force deflection curve, in one diagram.
Thank you very much for the question. So actually that has been something we have been thinking about and also have done some tries. However, it is really difficult to cast a sample with this really small void. So we did have some trials, and it's really difficult to have a good formwork which you can get out afterwards over 2 meters with this really thin void. So it's something we have in mind, but currently it's not been done yet. The fiber and the concrete interaction would might change a little bit if we have the fibers directly in the concrete. However, as I mentioned before, it does make it quite hard to use these large fibers. And we do have, due to our set-on-demand material system, we do have quite a fluid mortar coming out of the extruder, which is then quickly accelerated. So we have quite a good bond. So the pump normally did not jam. We did have in the beginning some problems with an overheating of the pump, but no jamming of the pump. So because we placed the fibers not with the concrete but separately, we did not have any problems with the pumps. And for the curing, we simply placed plastic foils over the beams after the production, and then left them like that. So we did not apply any curing agents or anything like that. But we did not have any shrinkage cracks that we could see.